Is going on, my algebros? In this video, I'm going to show you how to test some equations for symmetry. Alright, let's first go through this table. The first type of symmetry we're going to discuss is x-axis symmetry. As it says here, we're going to replace y, and let's fill this in together, with negative y. And the reason for that is because we learned earlier that if an equation has x-axis symmetry, then for each point that's on the graph, xy, there is a corresponding point on it with the coordinates x comma negative y. Alright? Yes. So that's why we replace y with negative y when testing for x-axis symmetry with an equation. For y-axis symmetry, we're going to replace x with, you guessed it, negative x. Alright, similar reasoning here. If an equation has y-axis symmetry, then for any point that's on the graph x comma y, there's going to be a corresponding point with coordinates negative x comma y. Alright, so that's why we replace x with negative x when testing an equation for y-axis symmetry.
Another one.
Alright, origin, glad we're at this one now. Okay, so origin symmetry, we're going to make two replacements. We're going to replace x with negative x and y with negative y. And for sake of completion, that's because if a graph has origin symmetry, then for any point xy that's on it, it's going to have a corresponding point with opposite coordinates, negative x comma negative y. Alright, so you have to make two replacements.
Yikes!
Now here's the shtick. Okay?
Yeah, boy.
It's not enough just to plug these negatives into the equation when doing your tests. We do have to make some simplifications, as it says here to the right. Upon making your replacements, you have to simplify.
Bruh.
And here's the thing. If the simplified equation is the same as the original, then you better believe that the equation has the type of symmetry that you're testing for. Alright, here's our first equation, y squared equals x plus 16. And my approach here is going to be a table approach. Now, as you might already be aware, I am not the world's greatest table maker.
Stop whining!
So please bear with me as I make these column headings. We got x-axis. We're also going to do a column for y-axis. And a third column for origin. Aren't you glad I included that? Alright, I'll stop. Okay, so these are the different types of symmetry that we're going to test for. Now with x-axis symmetry, one thing that you want to recall is that in order to test for x-axis symmetry, we have to replace the variable y with negative y. So anywhere that we see y in the equation, we'll substitute in negative y, and we'll have to simplify. Now looking at this equation here, we've got y squared on the left. And that's the only place where we see the variable y. So here we go. I'm going to use parentheses, which are important here, since we have a negative that we're plugging in.
Negative.
So that'll be negative y squared equals, we'll leave x alone, as well as the positive 16. So that's what the equation looks like with negative y plugged in. Of course, we're going to simplify according to the order of operations. We'll square this negative y. That turns into a positive y squared, equaling x plus 16. Now something you'll notice here is that this equation that we ended up after simplification is the same as the original, or the OG equation. So what that would mean
What do you mean by
is that our equation has x-axis symmetry. So let's just go ahead and note that. X-axis symmetry. Let's test to see if it has y-axis symmetry. And in order to do that, we have to replace x with negative x. So anywhere we see x in the equation, we replace it with negative x.
Negative.
Let's go ahead and do that. So we'll leave y squared alone on the left. And on the right, we'll sub in negative x using parentheses, even though they're not necessary here.
Nope.
Well, that's okay. And we'll simplify, which it's kind of nice in this case because simplifying just means remove the parentheses and we get negative x plus 16.
I just hope she don't wanna leave.
Now, this does not match the original equation because we're off by a negative sign right there. Hit like when you see it. Anyway, if there's anything that's different than the original, no matter how big or how small, then it does not have this type of symmetry. So give y-axis symmetry the buzzer, or the price is wrong horn.
Oh, sorry.
Alright, so no y-axis symmetry. Let's check for origin, which of course we have to make two replacements, y with negative y and x with negative x.
Bruh.
So we'll go ahead and do the replacements in the equation. So we're going to have negative y quantity squared on the left equaling negative x plus 16 on the right. So yeah, if you're, looking ahead and thinking, well, didn't we already do some of this work? The answer to that is yes, we did. Yep. So it's kind of a blending of the two tests, x-axis and y-axis. But it's still a good idea to check anyway. Plus, you can never get enough algebra in. But anyway, I do recommend testing all equations for all three types, just to be on the safe side. At any rate, we'll simplify. Y squared equals negative x plus 16. And we can give origin symmetry the buzzer as well.
Oh, sorry.
So it looks like the only type of symmetry this equation has is x-axis symmetry.
Emotional, damn it.
Alright, we're going to test another equation for symmetry. So here comes a table.
Come on now, dog.
X-axis. So we'll make a
Come
column for
on,
that type of
man.
symmetry. We'll do one to test for y-axis symmetry. And, you guessed it, origin.
Yikes.
By the way, I threw a frisbee one time and it never came down. Symmetry.
I think after a while, you just realize that it's part of the job.
Alright, sorry about that. Okay, well, let's recap some details. To test if an equation has x-axis symmetry, we replace y with negative y, y-axis symmetry, x with negative x, and then we do both replacements to test for origin. So y with negative y,
Negative.
and x with negative x. Okay. Alright, so let's test for x-axis symmetry. So anywhere that we see the variable y, we're going to replace it with negative y. So we'll do that right here. We're going to have x squared plus 2, and let's use some parentheses, times negative y minus 9 equals 0. And we'll go ahead and simplify this, which basically amounts to multiplying the positive 2 to negative y. And we end up getting x squared minus 2y minus 9 equals 0. Now, because this does not match the original equation right here exactly, then this equation does not have x-axis symmetry.
Nope.
All right, so Price is wrong with that one.
Oh, sorry.
Okay, so we'll test for y-axis symmetry. So again, we replace x with negative x.
Negative.
And in this case, we have x squared. I'll use some parentheses. So negative x squared plus 2y. We'll leave that y alone since we're only plugging negative x into x. Minus 9 equals 0. And we'll do the order of operations here to simplify. Negative x squared based on PEMDAS. Please end my day at Schoolcraft. And negative x times negative x is positive x squared plus 2y minus 9 equals 0. And you'll notice that this right here is the original equation. Therefore, we've stumbled upon some symmetry. We've got y-axis symmetry. Woohoo, there it is. Alright, Price is right with that one. Okay, so let's go ahead and make both replacements and see what we get. We'll have negative x into the variable x plus 2 times negative y
Negative.
minus 9 equals 0. And we'll go ahead and simplify. So we'll have to square the negative x and multiply the positive 2 to negative y, thereby getting positive x squared minus 2y minus 9 equals 0. And this is the same result that we got when we tested for x-axis symmetry. But regardless, it is not the original equation, therefore there is not origin symmetry.
Sorry.
So it looks like the only type of symmetry this equation has is y-axis symmetry. Alright, and there it is. Of course, if you have any questions, let me know. Otherwise, thanks for watching another one with me, folks, and I will see you in the next one. Have a great one.